All right, class, welcome. We're going to work through combining function transformations in this lesson. It's called lesson 1.4, but I think we might just retitle this one. Let's retitle this 1.3 part, because it's really not a whole new a new thing. It's just we're going to take what we learned about function transformations and push them all into one big function transformation. Okay, so recall we've got three kinds of function transformations. We've got translations, which move it left and right and vertically, up and down. We've got dilations, which stretch it horizontally or compress it vertically or horizontally, either way. And then we have reflections, which take the graph and flip it across the x-axis or flip it across the y-axis. And so we've got those kinds of three function transformations to work with. Turns out you can get a general transformation function that combines all of those different things into one big behemoth. So I called it T, capital T of X for transformation. And we've got C times F of 1 over D, X minus B, all inside of F. So we have F of 1 over D, X minus B, and then plus A. So what this does to the function F is it dilates it vertically by a factor of C. I'm going to try to underline each of these things. So we have the vertical dilation, which is coming from C. We've got a horizontal dilation, which comes from D. We've got a translation vertical by A, and then we've got a, lastly, horizontal translation by B. So that's going to move it right or left, positive or negative. Okay, so those are all the big chunks to it. A couple things that are important to note about this. These are actually really crucial, and I would write these down and put big stars by them or whatever. Otherwise, you'll find you'll make some errors when doing your transformations. Always dilate before you translate. Remember that? Dilate before translate. And the reason why you want to do this is because you want to think PEMDAS, right? Your dilations are multiplications. So they are multiplying your values before you're going to add values to it. So on the outside, it's pretty obvious. We get the answer, so F of whatever, that's our answer. So I'm going to underline this big answer right here. This box is the output to function F. What do we do next? PEMDAS. Multiply by C. That's a vertical dilation. What do we do after we multiply by C? Well, then we add A to it. So you can see for the vertical stuff, we're for sure following PEMDAS. Now for the horizontal stuff, the stuff in the inside, it's less obvious. It looks like you're supposed to subtract before you multiply because of PEMDAS, but actually follows the reverse order. And we'll talk about this at the end of this lecture. That this stuff on the inside, all of this is going to follow reverse PEMDAS, okay? Whoa. But if you just remember the rule, dilate before you translate, then you're not going to dilate before translate. Another thing that's really crucial is you can treat horizontal transformations totally independently from vertical transformations. So you can do all your horizontal stretching and shifting, you can do all that stuff by itself, then you can tackle the vertical stuff. And remember, if you just dilate horizontally before you translate, you'll be fine. Dilate vertically before you translate, you'll be fine. But they don't talk to each other. What I mean by that is that if you do some horizontal stretching and shifting, you don't touch the y values for your points. The only thing that's going to change those y values are vertical stretches and shifts, okay? So you can just do them independently, do all the horizontal stuff and then all the vertical stuff, or do all the vertical stuff and then all the horizontal stuff, and you'll be fine, okay? So you can treat them independently. You can do the horizontal stuff first, then the vertical, or vice versa, as long as you dilate before translate. Okay. Reflections, drop my pen. Reflections occur at the same time as dilations. So you can do the reflection, because it's a multiplication. So you can do the reflection before you dilate, or you can do it after you dilate. It doesn't matter. Just make sure that you reflect before you translate. Similarly, because it's a dilation, it's a multiplication. It's treated at the same time. So reflect, then dilate, or dilate, then reflect. It doesn't matter which order you do it in. Then lastly is I want you to pay particular attention to, on the inside, we've got parentheses around x minus b, which is to say that if there is a horizontal dilation factor, then you need to factor it out, okay? You need to factor it out from the inside. Otherwise, you'll be dilating, or you'll be translating incorrectly. Your translation horizontally will be wrong if you don't factor out d. Okay, so it's important that if there is something in there multiplying and you also have a translation on the inside, that you do factor out d. I want to also note, I've been calling things inside and outside, and I may have not been very clear with what I'm talking about. All of this stuff in the red, that is the inside of the function. This is inside, okay? Because it's inside the parentheses, and so it's affecting the x values. It's affecting the inputs, the things you're plugging into your function. So the outside is the stuff that's affecting the outputs. That's like this, c times something plus a. So there's our outputs. This is the outside. So we want to start recognizing what's inside and what's outside of our functions. Which parentheses are talking about multiplication? Which parentheses are talking about inside or outside of the function? So these big parentheses, let me clear up some of this ink. Whoa. What just happened? Okay. Go back. Okay. So let me clear up a little bit of this ink and we'll find it'll be easier to see. So these big parentheses here. So this, for red, for inside, this is denoting what is inside our function, okay? So that's the inside, 1 over d times x minus b. The outside stuff is all of this stuff out here, okay? So we have a c times a, or c times our output, and then the plus a over here. So that's the outside of the function, okay? These parentheses inside, these mean multiply. Multiply, like usual. And the red parentheses do not mean multiply. The red parentheses do not mean multiply. I want to emphasize this again. They mean inside. They mean what's the input. Red parentheses means what is their input. The purple parentheses that I've highlighted now, that does mean multiply, so you can factor like you would normally. Okay? You cannot factor the x's or the inputs out of the function. They stay inside the function always. They stay inside the parentheses. All right. Whew. Okay, let's do a couple examples. So let's take a look at a simple one. Here's our function 2x plus 1. That's a line, linear equation. And let's graph 2f of x plus 3. So how do we get g from f? Well, we double all the y coordinates, and then we add 3 to them. So this is a vertical dilation by 2, and then a vertical translation by 3. PEMDAS should remind you the order we do these things. Dilate, translate, not the other way around. So you multiply your outputs by 2, and then you add 3 to them. So here we can see some points. 0, 1 would be on the graph. Because you plug 0 in, you get 1 out. So 0 in, 1 out. Boop. And so that says f of 0 equals 1. So now if we were to plug 0 into this other function, g of 0 equals f of, 2f of 0 plus 3. So what does that say we do? Well, we multiply the output of f by 2, and then we add 3 to it. So this is 2 times 1 plus 3, which is 5. So you can see this point traveled to 0, 2 by the dilation, and then 0, 5 by the translation, and that's where it ended up at the end. And the point 1, 3, well, if we double its y, then that gets us to 1, 6. And then we add 3 to that, so that takes us to 1, 9. So let's take a look at the graph. All right, so blue is our original. So this is 2x plus 1. And then red is g, which is 2f of x plus 3. And so you can see that this y value that was at 0, 1, this guy, we multiplied it by 2, which sent it up to 0, 2. So that goes to here. And then we added 3 to it, so then that ends up going to there with the plus 3. So that's plus 3. This is times 2. So we multiplied it by 2 and then added 3. And then this point over here, which is 1, 3, we multiply it by 2, so that takes us to 1, 6 times 2, and then we added 3 to it. So then that takes us up to 1, 9. Okay? So that's how you get there. So look at another example. Let's say our starting function is x squared. Let's graph g of x, which is negative 2 f of 2x plus 2. Now there's a lot going on. We're just going to tackle each thing one at a time. And remember, always dilate before you translate. Okay, first factor out 2 from the inside to get this expression, which looks a little bit different. I want to be very clear that we are pulling the 2 out. So I put those parentheses there so that we can see what the transformations are more clearly. What are our transformations? Let's list them all out. We have a reflection across the x-axis. Let's highlight which one that is. So that's this minus sign right here. That's what's giving us the reflection across the x-axis. Then we have a vertical dilation by 2. That's this 2 in front of the f. So boom, that's what's it's going to dilate it vertically by 2. We have a horizontal dilation by a half. So that's that 2 right here. And then lastly, we have a horizontal translation left by 1. And that's this x plus 1 bit right here. So that's the adding 1. So now that we've listed out all of those different transformations, we just can tackle them one at a time, dilating before translating. Okay, so let's look at some points and where did they go. We have the original x squared over here. So let's track some points. So 0, 0 is the easiest one to find. 0, 0. When we reflect it across the x-axis, nothing happens to it. When we vertically dilate, nothing happens to it. When we horizontally dilate, nothing happens to it. We've done the first 3. And now we translate it left by 1. So where does it end up? It ends up right here at negative 1, 0. So now it's at, let's use the red for that. Now it's at negative 1, 0. So 0, 0, 1 to negative 1, 0. Now a harder one to find out where it went. Let's look at this one, which is 2, 4. And let's try to plot its journey. It took a long journey to get to where it is on the red graph. So let's walk through each of these steps. I'm going to use a different color for each step. So reflection across the x-axis takes it down to 2, minus 4. So now we're down here, 2, minus 4. A vertical dilation by 2, that's a blue one. Vertical dilation by 2, that's going to multiply its y value by 2. So 2, negative 4, now it's 2, negative 8. So it's down here. So now horizontal dilation by a half. So that means it was 2, negative 8. Now it gets x coordinate gets dilated by a half, so now it's at 1, -8. So now it's right there. And then last but not least, a horizontal translation left by 1. So now it's right here at 0, -8. Its final resting place. Okay? So that's where it ended up, 0, -8 after each of those transformations. Reflection brought it down here, and then vertical dilation brought it to there. Horizontal dilation brought it to here, and then lastly the horizontal translation left. So you can do this for a bunch of points, and then you'll find you end up getting that red graph that we have down there. Okay, let's look at another example. Now we're going to start with the answer graph, and try to work backwards. What is our transformation? How could I write G in terms of F? So we're starting with F, which is the blue graph. This is F of X, and we're going to try to get the red graph, which is G of X, by doing transformations on the blue one. Okay, so let's just start doing stuff to get it to look like the red graph. So what's one thing you could do? Well, I know that G of X is going down and to the left, so I think I need to do a reflection here. So let's just try a reflection. So if we do a reflection across the x-axis, that gets us kind of close. We also need to reflect it across the y-axis. So let's do that too. So once we reflect it across both axes, looks like we've got a much clearer, closer version of G of X. Alright, so we would be going through these points if we were doing those two reflections. So at this point we are negative f of negative x. Okay, after two reflections. Now let's take a look at some points. I need to get this 0, 0 down to -2, -2. And since 0, 0 doesn't move when we do dilations, we know it's going to go down left and right, left 2 and down 2 to get there. So let's drop this function into the right location so that the 0, 0 ends up being here at -2, -2. So far now we've got a two reflections, and then translate left 2 down 2. Because I remember 0, 0 moves nowhere under dilation. So I got to get it down there. So let's clean this up a little bit. So we'll clean this up a little and see if we can't figure out what our dilation is if we need to dilate it at all. So we're now here, and we went over 4 up 2, so now we're going to go over 4, left 4, down 2 to find the next point. So we're here, and so we're going to be zooming like that. So it looks like we need to do a dilation on this to make it the right kind of height vertically to stretch it out. So this looks like a distance of 2, and on the red graph it's actually a distance of 4, so we need to get a vertical stretch factor as well. So if we get a vertical stretch of 2, that's going to make this twice as tall, and then we'd be right where we want to be. So we have a vertical dilation by 2. And that's all of them. So we have a vertical dilation by 2, 2 reflections, and translate left 2 down 2. So let's go ahead and write the whole thing out. I'm going to write it up here in the upper right, or I'll just write it over here in the white space over on the right. So we have a vertical dilation by 2, so G of X is equal to minus 2 with the horizontal the reflection across the x-axis and the vertical dilation, f of negative x plus 2. Oh, we'll just write it next to G of X. So it equals negative 2 f of negative x plus 2 to move it left, and minus 2 lastly to move it down. So we've got those two reflections right there with those minus signs. We've got the vertical dilation with the 2. We've got our horizontal translation left 2 and our vertical translation down 2. And lastly, the domain and range. So the domain and range is going to be, if we look at the graph, we can read it off. It's just from negative infinity to negative 2. And then the range, so this is the domain, and then the range is going to be also from negative infinity to negative 2. And so you can see the original function's domain and range did get changed by this transformation. Okay. All right, let's look at one more case. So this one's a bit simpler. Suppose the blue function is the graph of f, and the red function is the graph of g, which is a transformation of f. So we've got f of x, and then we've got g of x is red. There's g of x. We need to figure out what is g in terms of f. So let's try to start dilating and translating this till we get into the right shape. So one thing we can see is that the width, kind of the width of g, is from negative 4 to 8. So if I figure out how big that is, negative 4 to 8, that's going to be, that's a width of 12, right? That's all the way from here to here is 12. And if I were to measure that width for the original function, I can see its width is only 4. So that's only 4 for the original function. So I need to get my width from 4 to 12. So that means we have a horizontal dilation by 3. By 3. Because we had started with something that was a width of 4, and we went to something that was a width of 12. 12. So it's bigger, and so that's going to be a dilation by 3. Now let's look at the height, see if the height has changed at all. So the height of our function is measuring from here to there. That's a height of 4. So this one was a height of 12, width of 12 from here to here. And that was a width of 4. Now we have a height of 4, and the original one went from negative 2 to 2. So that was also a height of 4. So there's no vertical dilation. So we have no vertical dilation for this one. So we have a horizontal stretch, and then we just have to get it into the right place. So let's identify some key points. Now that we've determined we've got this horizontal dilation, I can erase all this work. So let's identify some key points, see where those go. So let's take a look at this point 0, 0. Where did that end up? Well, it's this point in the middle of the graph where it starts to kind of go up and the other part starts to go down. I can identify that middle point is right here on the red graph, the transform. So I can see it's moved right to and up to. So I've got a translation right and up by 2. So is that going to get us the right shape? Let's just test it out. So I expand this by a factor of 3. So that's going to get me a shape that looks like this. Like this. Boom. And then we move it right to and up to. So this point moves right to and up to, and up to. So that takes it to here. This point moves right to and up to, so that takes it to there. This point moves right to and up to, so that takes it to there. Right to up to there, right to up to there. And so yes, we do in fact get the shape after doing the translation right to up to. So that's all that we have for this one. So let's just write it out. That gives us g of x equals horizontal dilation by 3. That's on the inside. No vertical dilation, so we just start writing f of horizontal dilation by 3 is 1 over 3 x minus 2 That's our translation right to, and then up to plus 2. So that's our function. F of 1/3 x minus 2 in parentheses plus 2. Oops. And the domain and range of G is identifiable from the graph. You can just see that it goes from -4 to 8. So that's the domain. And the range goes from 0 to 4. Okay? And so the range got affected by that translation up. The domain got affected by the dilation and the translation. Both of those affected the domain and range. All right, that's probably good enough for today. The next time I'll have a short video about why the insides reverse PEMDAS, and then we'll dive into function compositions after that. Okay?